This is a video on specific heat capacity, which is part of the third module in the Year 11 physics course, Waves and Thermodynamics. Okay, so what is specific heat capacity? Best way I can define it, it's basically the amount of energy needed to raise the temperature of 1 kilograms of a substance by 1 degree Celsius. Okay, otherwise known as 1 Kelvin. Now, Kelvin is another way of measuring temperature. So there's temperature scales like Celsius that we're all familiar with here in Australia, of course. Celsius, there's Fahrenheit, that's used in countries like the States. There's Rankins, and there's Kelvin. Kelvin is used internationally by physicists. It's just a common ground for them to all use the same temperature measurement because there's obviously different countries that use different scales of temperature. So Kelvin is just a scale that's used by all physicists around the world. Okay, so it's basically the amount of energy needed to raise the temperature of 1 kilograms of a substance by 1 degree Celsius, 1 degree Kelvin. And I should also mention here, I should stress, without a change in phase. What does that mean? Well, think of a slab of metal, some volume of metal here. It's basically that metal retaining its state, which is solid in this case. Okay, so long as it doesn't change form, specific heat capacity can be measured. So I'm going to derive the mathematical relationship for specific heat capacity as follows. I'm going to start off with this. Okay, so temperature. I'm going to start off with temperature. So the temperature of a body, okay, body is some substance, okay, temperature of a body, let's call it T, capital T. It increases in direct proportion to the amount of heat energy put into a substance. Okay, what does that mean? Well, temperature is a measure of how much heat energy a substance contains, right? So the more heat energy I give something, the higher the temperature, right? For example, mercury thermometers. The reason why the mercury goes up, there's a saying that people say, they used to say back in the old days, mercury's gone up, that means that the temperature is increasing, okay? Because the mercury in the glass thermometer is expanding, okay, because of the temperature. Well, mathematically, here's what it means. Here's how I can express it mathematically. So temperature, so delta means change in temperature T is proportional to Q. We use Q in physics for heat energy. Okay, it comes from somewhere, I don't know where. So yeah, temperature is proportional to heat energy. Okay, that's what this symbol here means, proportional to. We also know that temperature is inversely proportional, which means we divide by inversely proportional to mass, the mass of a body. Okay, M for mass. And I should stress here that the statement that the temperature of a substance is inversely proportional to its mass is not generally true. Okay, because temperature is a measure of the average kinetic energy of the particles in a substance. Okay, while mass is a measure of the amount of matter in the substance. And in reality, the temperature of a substance is determined by several factors, okay, including the amount of heat energy added or removed, the specific heat capacity of a substance, and things like its thermal conductivity, okay, how well it can conduct heat. So the mass of the substance itself doesn't directly determine its temperature. But it's worth noting that in some cases, some specific cases, such as when comparing two objects of the same material and equal thermal energy, the object with the greater mass, let's call it 2 sub n, as opposed to the same object, okay, same substance with a mass n, the object with the greater mass will usually have a lower temperature, okay, and that's because a larger mass requires more heat energy to raise its temperature okay, by the same amount as opposed to a smaller mass. And this phenomenon is related to the concept of specific heat capacity, which is the amount of heat energy, as I mentioned before, required to raise the temperature of a substance, 1 kilogram of a substance by 1 degree Celsius. Okay, so let's put these two relations together. Let's put these two together, and we will get this proportional to Q divided by M. Now, how do we turn this proportionality statement into an equality? Okay, to add an equal sign. Okay, so here's what we do. Okay, we need to put in a constant. Constant is another word for saying number in physics. Okay, let's call it C. Now, C is the specific heat capacity. Actually, before that, let me just rearrange this equation here. So let's get C by itself. So how do I do that? Take the delta T down there in the denominator, Q divided by M delta T. This relation is the specific heat capacity of a substance. This is how you calculate it. This is the formula, where C, the constant, is known as the specific heat capacity. What are the units for specific heat capacity? Well, Q is measured in joules. It's the amount of energy supplied, okay, to the substance, to the body. M is the mass of the substance in kilograms. Delta T is measured in Kelvin, temperature. So therefore, the specific heat capacity has units of joules per kilogram per Kelvin, okay, because there's a divide there, that's why. Okay, noting that 1 degree Kelvin is 1 degree Celsius. Okay, and then you can rearrange this in different ways to find, let's say, Q, to find M, dot, dot, dot. Okay, and that's the idea of specific heat capacity.